In our local neighborhood, celestial mechanics feel settled. You have a star, orbiting planets, and moons orbiting those planets. Beyond our solar system, we've documented over 6,000 planets, but the official count of confirmed exomoons remains exactly 0. The search gets complicated when we encounter bodies that refuse to fit into neat categories. Take the brown dwarf, a sphere of gas dwarfing standard planets, yet it lacks the internal pressure needed to trigger sustained nuclear fusion. It falls short of stellar ignition, leaving it a dimly glowing, supersized sphere. Our Earth-centric dictionary categorizes the cosmos based on what we see out our own window, but looking deeper into space, those rigid definitions begin to fail. About 72 light-years away sits the CD 352722 system. At its center is a red dwarf star, radiating at about half the mass of our Sun. Locked in a wide, eccentric orbit around that star is a brown dwarf. It traces an elongated path that takes roughly 5,000 years to complete one single revolution. Recently, astronomers analyzing this system detected a third object. It is locked in a tight orbit around the brown dwarf, rotating every 170 days. And it is massive. The data indicates this new object contains at least the mass of Jupiter. The International Astronomical Union relies on specific mass limits and orbital dynamics to classify celestial bodies. But here, a Jupiter-sized gas giant orbits an even larger failed star. It fits neatly into neither the planet nor moon category. Science has stumbled upon an architectural arrangement so unusual that we lack the vocabulary to accurately label it. Finding this anomaly required pushing current technology to limit. The discovery comes from the European Southern Observatory's Very Large Telescope, a massive array positioned high in the Chilean desert. This chart shows the difficulty of the observation. The dotted line represents the precise slit of the telescope's spectrograph, allowing astronomers to isolate the faint light of the brown dwarf from the glaring primary star. The target object itself is entirely obscured, making direct photography impossible. To find it, researchers applied the radial velocity method. They analyzed the light from the brown dwarf, looking for microscopic color shifts. If an unseen companion is orbiting it, the gravitational pull of that companion will cause the brown dwarf to wobble. As it is pulled slightly away from Earth, its light stretches toward the red end of the spectrum. As it is pulled closer, the light compresses toward the blue. By tracking these color shifts, the instrument recorded a repeating wobble. The brown dwarf was being tugged back and forth on a predictable cycle of 170 days. By measuring the amplitude and timing of that wobble, physicists can calculate the exact mass and orbital period of a giant object they will never directly see. The radial velocity measurements allow for two distinct configurations: a single massive object on an eccentric orbit, or two smaller satellites locked in a specific resonance. Researchers ran both scenarios through orbital simulations. The two-satellite model proved highly unstable, consistently ejecting one of the objects and tearing itself apart within 500 years. That left the single eccentric satellite as the only mathematically sound explanation. The surviving model revealed a massive ratio. The satellite is roughly 2.5% the mass of its host brown dwarf. For context, our Earth-Moon system is a high-mass anomaly at 1.2%, and the moons of giant planets are smaller by orders of magnitude. This architecture places a massive gas giant in a tight orbit around an even larger glowing sphere of gas, while both trace a centuries-long loop around a distant star. The IAU technically allows an object orbiting a brown dwarf to be classified as a planet, but that rule treats the host body in isolation, ignoring the system's wider, three-tiered structure. The research team proposes a new classification, the exosatellite. This term acknowledges the object's functional role. It orbits a larger companion like a moon, while recognizing a mass scale that matches our local planets. This distinction carries real physical weight. Over millions of years, the host brown dwarf will cool and drop in luminosity by 100-fold. Meanwhile, the central red dwarf star will keep burning at a constant rate. An object caught in that specific gravitational and thermal crossfire exists in a complex environment, one that a standard planet or a traditional moon will never experience. Confirming this discovery requires the next leap in optical power. The European Southern Observatory is currently building the extremely large telescope. With its 39-meter mirror, this facility will have the resolution to finally verify the CD 352722 signal and scan the sky for smaller targets. Astronomers suspect this single detection is a preview. As instrumentation improves, they expect to uncover an entire population of these massive exosatellites hiding in the glare of their hosts. The CD 352722 system proves that the universe operates with a level of structural diversity that ignores our attempts to categorize it. To accurately map the cosmos, we have to be willing to tear up our Earth-centric dictionary.